So wait 1 minute.
Good afternoon, one and all. I am Devashri Ghansham Bhakkar from Artificial Intelligence and Machine Learning branch. I am very privileged today to provide you with a briefing of our today's guest, Sk Subidh Ali sir, a notable expert in the field of hardware security and cryptography analysis. Sir is recognized for his significant contribution to the field of hardware security and cryptography analysis. His work has been published in prestigious conferences and journals demonstrating his expertise. Sir has conducted extensive research in DFA, which is critical area of cryptography analysis. His work includes differential fault analysis of two fish presented on the 8th International Conference Information Security and Cryptology in 2013. Also, it includes cryptographic hardware security and multimedia attack, an emerging threat model for cryptography hardware presented at the conference. It also includes advanced encryption standard. He has conducted DFA on AES, a widely used encryption standard, and improved differential fault analysis on AES 256 presented at the 4th International Conference in Cryptology in Africa in 2011. Differential fault analysis of the advanced encryption standard using a single fault at the IFIP WG 5th International Workshop on Information Security Theory and Practice in 2011. Also includes scan attack analysis. Work on analyzing scan attacks and countermeasures include scan attack in presence of mode reset countermeasure presented at the 2013 IEEE 19th International Online Testing Synopsis. This contribution reflects Sir's expertise in hardware security, cryptographic analysis, and vulnerability assessment. We anticipate that Sk Subidh Sir will provide valuable insights in the field of cryptographic analysis and hardware today. I now hand over the session to Sir. Thank you.
Thank you, Seetal, for a long introduction. Like you gave a lot. I mean, you read my entire CV, I guess. Yeah. So, may I know, like, what is the background of the audience? Like, these are faculty, right? Faculty in computer science. Divyanshi or Seetal, can you answer this? Am I audible?
Yes, sir, you are audible.
Yes, sir, you are audible.
So, these are faculty members, right? Audience.
Yes, sir.
Okay. Okay, fine. So, yeah, let me share my screen. So, yeah, although the theme of this FDP, Faculty Development Program, is on blockchain, right? So, now blockchain has got huge applications from cryptocurrency to your, the patta of your jameen, your lands that are being stored in uh, uh, lasers. Those are blockchain technology. So many states in India, including your Telangana, even Chhattisgarh, they have implemented this thing. The land records that are being stored in this blockchain. I mean, using technology like blockchain. So one of the key aspects of blockchain is the hardware. So now you must have heard, like as you are listening to many experts in the area of blockchain, and it started on 9th, right? Almost like 2 days over, and you keep listening on blockchain technology, and you must have listened to multiple news, multiple facts on blockchain, where a person having close to few $1 million, he lost his money. The reason is $1 million in cryptocurrency, and he or she lost the money. And the reason is he lost the token, the crypto token, that is majorly your private key. If the key is lost, that means uh, your identity is lost in cryptocurrency domain, right? So now one solution we will come up with, like we are human being keep forgetting things. Sometimes we write our password in some place, even we forget where we have written the password, right? And the file or the book or the copy we used to write our password, that may be lost. So one solution people came up with is crypto token. So in crypto token, it's like a regular your USB dongle, like this one, this USB dongle. Okay, inside this USB dongle, you'll have a microcontroller. So now, in this microcontroller, you'll have a secure chip which will store your identity. That's your secret key and the detail required for log into your like any cryptocurrency applications. So those information are stored in a dongle. So now this dongle supposed to be very secure against a lot of attacks, cyber attacks, hardware attacks, and blah blah thing. Now once you have this sort of dongle, now the biggest threat is not about cyber attack, because most of the time these dongles are not connected to the internet. So you'll be carrying this dongle with you, right, like a key ring. And now the moment you want to do some transaction in cryptocurrency, then you'll be use it and log into the system, and then you will get the transaction done. So once you have this device, the major challenges you face is in the domain of hardware security. So my talk is entirely focused on hardware security. I'm not going to talk about your blockchain technology, because you have already listened to. You are going to listen many such thing again in the subsequent part of this FDP sessions. So what I'm going to talk about, like what is the hardware security aspect of this crypto tokens. We are majorly focused on crypto tokens. We are not focusing on your systems or your cloud where you are running your cryptocurrency entire software, where it's not focused on the devices where you do the mining and all other things, where you keep your ledgers. That is not our target. Our target is this particular dongle that is being used nowadays by many people, by many organizations. They provide you the dongle. Now with the help of the dongle, you can access your system. So now, so in the hardware security, basically in this domain, what you have, your software is secure. For example, you use RSA 2048, or you will use ECC, elliptic curve cryptography, where you have sufficient size of key length, and these crypto algorithms are sufficiently secure against known attacks, right? So in that context, we say the moment you are using any modern security system like blockchain technology, like cryptocurrency, like Bitcoin, then the system are quite secure, because the algorithm, the security protocol you are using, those are already proven to be secure. But when these algorithms are running in a hardware, that time the security can be violated. So my talk is on this hardware security. So we will be focusing majorly one aspect. There are many aspects of hardware security. I'll go one by one. So uh, yeah, so if you consider hardware security, that has got two major domains. So one domain is the sidechain analysis, where you precisely break into the cryptographic system and steal the secret key. Now, another aspect, we call it IP security. Suppose you design this crypto token, and then you have, that is your IP, right? That the hardware IP is your IP. Now, the moment you send it to some third party foundry, like most of the chip, like you faculties are, you are familiar with Raspberry Pi, Arduino, right? All these chips are actually manufactured in China. So the moment you get a chip from China, you cannot trust it. No one in this world can trust this, because uh, most of the Chinese chip are manufacturing. I mean, the manufacturing place, the fab lab, those are controlled by Chinese government. And if you remember that we used to say long back, we used to say Linux is the most secure operating system. Then later on, even Linus Torvald came up and he told that when he was developing Linux system, Linux operating system, actually US agency came to him and ask him to induce some backdoor into the operating system so that US agency, if required, they can use it. So that that information came to a news report, right? So it shows that when when any big shot company in US they are developing something, so they'll have a tie-up with the US security agency. The same thing is true in China. So the moment they manufacture any software or hardware, they will have tie-up with their security agency. If it is a hardware, they can induce hardware Trojan. So you you also familiar with one of the server being used in many of your server rooms. That server is provided by NetWave technology. So those server name are Tyrone, right? So Tyrone, the mother company of the Tyrone, they were blacklisted from US. You know the reason behind that? They were giving a huge cloud infrastructure to Pentagon directly, and the tender was done by uh, this Amazon. So Amazon do a lot of cloud technology, and they were supposed to provide these cloud infrastructure to Pentagon. And when they provided, they use this Tyron servers. And what later on US agency figure out, this Tyron server, some of the server has got tiny chip, and those chips are being used to tap the information passing through, your machine. So using that chip, the, the hackers who are sitting in China, they can actually tap into your system, and they can hack into your system. And knowing this incident, after knowing this incident, this first of all, this Amazon, they lose the tender, and this Tyrant company actually blacklisted from US. Right now, none of the government agency in the US, they are going to buy. None of them going to buy this Tyrone servers, because these are actually manufactured in China and they have a lot of security vulnerability. So my point here, when you have your own design, like if you are if you know a bit of chip design and all, you must be knowing a company called ARM. But ARM does not manufacture a chip. So whatever Raspberry Pi you have, your mobile phone you have, this the Snapdragon chip, right? That's an ARM chip. So ARM chip, it doesn't mean that ARM actually manufacture those chips. Those chips are being manufactured in the foundry. We have altogether four foundry in this world. One is with Intel, one is with TSMC, one is with Global Foundry, and the last one is with China. So now, because Chinese chip manufacturing is much more cheaper, so most of the company will approach them. Even if you have iPhone, that iPhone is actually manufactured in China, and it is designed in San Francisco, and the design goes to China, it is being manufactured there, and it goes back to US and packaging and done, then it goes to you. So now everybody is going towards China to manufacture in a cheaper way. So now if you have some design, some chip design, so eventually you have to also approach Chinese manufacturer. The moment you send your design, what vulnerability i- you can have is that, like, the moment you send a design, they can add additional chip into it, additional design into it, that we call hardware trojan. So that can be added during the fabrication process. So once your chip is manufactured, you have no clue what has been added. Even if you do all sort of testing, functional testing, all sort of testing, you will never figure out what Trojan has been added. And this Trojan will be only triggered by the person who actually inserted it. So now the point here, the moment you send something to manufacture in China, some chip specifically, you cannot trust it. So that area is the domain of the IP security. So your design being modified in some other country, your design can be stolen. You send to them, and then what they can do, they take the design and they modify it, and then later on they can claim that this is their own design and they can manufacture chip based on that design. So in that case, you will lose the revenue. So that domain is called IP security. In the side channel domain, there are so many different side channel analysis thing. So one of the analysis that was my key research area during my PhD time. That is called fault analysis. So like when you manufacture a chip, that chip has to be tested for possible fault during manufacturing process, right? So that that process is quite well known in the domain of VLSI. Those people work in VLSI, they know about hardware faults. But you can intentionally induce fault into a running uh, quite good chip. For example, you have a phone, right? You can intentionally induce a fault. For example, the supply you are giving to the phone, it could be around like 3.5 to 5 volt, right? So if you give the supply voltage less than 3.5, it will start producing erroneous result because your chip start giving you faulty results. So that is called intentionally fault induction. So now you can use this idea, intentional fault induction, and you can induce fault into cryptographic chip. For example, if you know about AES cipher, if you know about RSA cipher, ECC cipher, in all the cipher, if you are able to induce targeted fault into a particular operation, then you can actually break that cryptographic system. So in this talk, I will talk about how to break a cryptographic system like AES. So AES, it's like still it is unbreakable. So it's been like it was proposed back in 1999, right? So it's almost 20 years, but still it's remain as unbroken. No attack is there which can actually break the entire crypto system with its all full round. For example, AES 128 you have, it has got 10 round. So there is no attack that breaks 10 round AES. So my subsequent talk is about fault attack on AES. Then you also have timing attack. So this timing attack, you know, if you follow the news related to cyber attack, then you must have heard like 5-6 years back we used to have an attack that's called meltdown attack. So this meltdown attack actually crippled most of the company chip. So like Intel, Qualcomm, they raised their hand back in that day around 2018 or 19. That attack came up, and they raised their hand that they said that we have no solution right now to protect against this attack. So most of the chips are vulnerable to meltdown attack. You know how this meltdown attack works? It basically uses your cache memory. So most of you are faculty in computer science, I guess. So now like many of you learn this, computer architecture during your BTech time. Some of you are teaching computer architecture. So one of the key component in computer architecture is the computer hardware, is the cache memory. So now, if you're running some program, right? So the program is needed by your processor. So processor means that is your core, right? Nowadays, one processor is having multiple cores. So quad core, like Core i5, Core i7, they have multiple cores. Started with dual cores. Now you have, like if you have server, it goes up to 32 core, even 64 cores. So each core you can treat as single processor. So now the program you're executing, it is executed one instruction at a time. So each instruction has to be fetched by this processor inside it, right, from the RAM. So now this fetching takes lots of time, right? So that's why they put high speed memory, that's called cache memory, in between. So now one thing is quite clear, all of you know that if the instruction you're looking for is in the cache memory, so that fetching will be much more faster. If that instruction is not there in cache memory, that is much more slower. Is it clear that it's already familiar to all the computer scientists, right? So cache memory is there to speed up the processing, the fetching process. So now the instruction the processor is looking for, if that is there in cache memory, so that means that execution time of that instruction is much more faster than that instruction which is not there in cache memory. So we call it cache hit and cache miss. Now, if I'm an attacker, so what I can do, suppose you are running a code in the same machine where I'm also having access. So what I can do, I can check what instruction you executed, right? So by just figuring out if I just run that instruction, okay, if it is a hit, cache hit, that means that instruction you actually executed. Because if you see the cache memory management, it's like right through, right? So whenever you fetch the instruction, it has to be on the cache first, and then it goes to processor if it is not there in the cache. So if I get a hit, that means I'm 100% sure you use that instruction just now. So now that is called head. So now based on that, I can figure out in the context of data, right? I can figure out the intermediate result of an encryption, and then I can, based on that, I can figure out the secret key. So that is what timing attack they do. So this is a very well-known area of hardware security, and we call this timing attack. So some of one aspect of this is power analysis, but timing, I mean, like one aspect of this is cache timing attack. So timing attack is not dependent on cache. Whenever you have this variation of timing based on your architecture or network communication, so you can misuse this timing variation and you can figure out some information, extract some information from the system. And one more side channel aspect is the power. So these three are the most mostly used, you can say. So power analysis, what they do. So if you guys worked a bit of power management of a chip, so you must be familiar on this aspect. So in power management, right? Suppose you have multi-core environment, two core running. So the moment you have a code that has to be splitted into two core, then only this two core will be running. Otherwise, one core will be running, right? But suppose I don't know what is running inside, but I can tell you that whether you are running a code with multi-core environment, I mean like with multi-thread environment, or you are running your code without multi-thread environment, just by tapping into your power consumption, right? So because if you're using two core, you will be consuming more power. If you're using one core, then you will be using less power. So I can see that this power consumption, I can plot the distribution, and in that distribution I precisely pinpoint, okay, during this time you use single core, during this time you use multi-core. So now I can even do much more fine tune into it. I can even say, okay, which core you are using, right? So what I can do, I need a lot of data from your computer, like you are running many data and I have some information about it. Like sometimes you are using this core, sometimes you are using the other core, sometimes you are using both the core. So now if I have all this power consumption and I have this information, like what time you are using what core, this is called, like, if you guys are familiar with machine learning, this is called level data. So if you have this level information, then I can take this data and now I can match with some captured data and figuring out, like, okay, this data is matching with which one. And based on the match, I can say, you right now for this power profile I have, so that is for that particular processor, and you are even running these kind of code. So these information I can fetch, extract even without looking into what is running in your computer. So the machine learning guys, if you do work in machine learning, so you are quite familiar of this thing that's called pattern recognition. So we actually do this kind of pattern in the power profile, and based on that we extract the secret key. That is called power analysis attack. So on top of that, you have also like scan attack. You also have EM attack, but EM attack is actually power attack. You also have acoustic attack. So acoustic attack, what they do, they listen. So when you run something in the chip now, so it actually emits some sort of sound, and you need really high-end sensor to capture those sound. So this has been shown in some Israeli lab. If you're familiar with security domain, then you must know Adi Samir. So this RSA, S is for Samir. The Samir is a big shot researcher in the domain of cryptography. So in his lab, one of his students actually developed this acoustic attack. So acoustic attack is basically like this power analysis attack, but the secret key they extract based on the sound wave rather than power wave. So these are these are one aspect of hardware security, where given a hardware chip, which is like, say, inside it is very secure, the cryptography is very secure, the application is very secure. But if you give it to the hardware security guy like me, so we can apply one of this attack, and we can, even if a system is very secure, but I'll extract the secret key from your chip. So now that means, like previously you were majorly focusing on the cyber aspect, the software aspect of the security. Now you have to focus more on the hardware aspect, because the hardware you are using, that hardware is leaking information outside. If you can tap into that information, then you can break the system. So this is what the fundamental in the IP security. Again, you can classify into multiple aspects, like hardware Trojan. I just mentioned counterfeiting. Also, I mentioned that, like, you send your design to somewhere, some foundry. There might be a bad guy who can take your design and sell it to some black market, and they can produce chip out of it. So you'll be losing your revenue, right? Because you spend a lot of money to get that IP, and later on somebody is using for free. Then IP reverse engineering is like very old domain, like where, like, you have a IC with you. Now, if give it to the reverse engineering company, there are a lot of company, well-known company, they do the reverse engineering for you. So you need to pay them, and you should have the authority to do the reverse engineering, that certificate. So if you give them the certificate that you have the right to reverse engineer, and if you pay the money, then they'll reverse engineer. So what they do in reverse engineering, suppose you design a chip, and that is your own proprietary design. You find out a technique, very nice technique, where suppose a microcontroller is doing much more faster than any other microcontroller of similar specification. So that is your design, right? So now the moment you manufacture the chip, so now you assume that once the chip is manufactured, nobody can see what is inside the design, right? But this guy, what they do, they'll remove. If you have the chip, you see, if you have this chip like this, so they remove the top black portion from the chip. Okay, now you have the metal layer. So in the metal layer, they'll take the very high resolution microscope and capture a lot of pictures, and based on that picture, they'll actually calculate the interconnection. So in the hardware domain, we call netlist. So even they can precisely tell you, okay, this is what the gate being used here. This is AND gate, NAND gate, NOT gate. So all the gate information, gate level information, even gate level information, they can provide you. So now you can precisely, even they have automated tool. Once this gate information is given, they can actually figure out what is the possible design, actual chip design. So that information they can extract, right? So, and in order to overcome this kind of reverse engineering, people have many solutions, like they use obfuscation technique, they use logic logging technique. So these are the two major techniques being followed in the domain of IP security. So now you see, like, this is the area where the company who actually develops secure chip, like Apple, Intel, and they lose a lot of revenue, because the moment somebody came up with an attack on your device, then people stop buying your device because your device is threatened. It's vulnerable. So either you have to come up with a patch, or you have to discard all those devices and give a new device to all the people who bought your device, right? But generally the first is the major option, because in your system, right, in your whatever operating system you're using, so once in a while you'll see the update, and that is the system level update. But most of the time we'll figure out the update is for the security update, right? Using the security update, what they do, recently figure out attacks are being patched. We use the term called patching. Patching means you had the security, somebody attacked and figure out that using, there are some vulnerability, using that vulnerability they can break into your system. So somebody figure out and they publish it, or this company themselves, they have their own security team, they figure out the vulnerability, now they will send you the update. In update, they will try to patch it. Okay, this was the vulnerability, now I'll overcome this vulnerability if you update the system. So now, see, once you manufacture, right, you assume that, okay, I manufactured the chip, so I spent the money, now I should get the return, I sell the money. But still you are keep on working, like, if there is an attack, then I have to patch it. So you are spending a lot of money. This is one way of losing revenue. Okay, another way of losing revenue is that somebody just attacked, and you did not know about that. So now you have to hire a lot of people, figure out what way to patch it, then you again send those patch information. So that is again a lot of money. So this chip manufacturer company waste lot of revenue in patching those things in both the domain, in hardware security and in the IP security. So, and this is an evergreen domain. I mean, till the day you'll be using chips, these kind of vulnerability will always be there. So the security versus defense is kind of cat and mouse game. This has been happening since the days of Adam, and now it is going on, and it will keep on going on since human being will be there, and who need some facilities and defense. So let us move ahead. So my if you look into my research area, I previously work on differential fault analysis, where you induce fault and break into the system. I worked on scan and analysis, where you actually misuse the test infrastructure when you manufacture a chip. So every chip will have its 25% of the chip used. I mean, that is a waste actually. That 25% is added just to test the chip. So if you have, say, 100 gate in your chip, so in this 100 gate, 75 gate is for the functionality, and 25 gates are for testing those 75 gates, right? So nowadays, whatever chip you have, that will have this additional chip module, which we call as test infrastructure. So now the moment you have this test infrastructure, that is for the tester. Now tester can misuse this test infrastructure, so you can impersonate yourself as tester, and if you have access to the test infrastructure, then you can break the cryptographic system. So that is what we do in the scan attack. And the test infrastructure we use is called DFT, designed for testability. And I also use IP reverse engineering, and that is specifically in the domain of logic logging. Let us not talk about logic logging now. So if you're interested, uh, you can look into my CV, and we'll get a lot of papers on this. So, and I also worked on microfluidic biochip. So earlier days, when you go for any sort of blood test, right? Um, that time what they do normally nowadays also, they'll use a syringe and extract some blood from your vein. So now what they do, what this tester, this like pathologist, so what they do, they'll have some test tubes, and they'll put the blood, and then lot of reagents, and then do a lot of chemical synthesis process, and based on some color at the end of the experiment, they figure out, okay, you have this, you have that, you have blah blah thing. Let us not go into what you have, right? So let us just figure out, this is a very complicated job, and it requires a lot of blood, because you see test tube, that is like our school days chemistry thing, right? So what happened is that, so people came up with this biochip. So now you must have seen in the medical shop, they have this blood sugar tester. So for the blood sugar tester, what they do, they'll just use just a prickle a bit using some needle, right? It's just a droplet, tiny droplet they'll take, and now that will be put into the chip they have, and then inside that it will automatically do that experiment, that adding reagent and blah blah thing, and then it will change the color, and then you plug it to your device, that electronic device that they'll give you with the system, and this will tell you what is the blood level you have. So in those devices, they use this kind of microfluidic chips, but exactly it's not digital microfluidic chips. So in digital microfluidic chip, as you can see in the figure, this basically, it's like your microprocessor 30 years back, even not 30 years back, maybe 40 years back, 50 years back, whatever your microprocessor would look like, it will have few hundreds of gates only, or maybe thousands of gates. So it was, now the digital microfluidic is in that level. So you can assume that 10 years down the line, this digital microfluidic chip will work like a microprocessor of today, where you have billions of gates. So now, what is a gate here in digital microfluidic biochip is simply one electrode. Where you put the droplet, it will move, it will create an electric field next to the next electrode. I mean, the electrode which is next to the droplet. If you have the electrical field, that will create a static charge and that will push the droplet towards the next electrode. So this way, you can actually automate and move the droplet from one place to another place, and then make it to mix with reagents, and all this thing can be done writing a simple code and automatically within a chip. So this is the logic is almost same as like the digital logic, right? So now if we have this chip, this is again a hardware. So what we can do, we can actually misuse this chips. We can launch hardware attack, and then we can manipulate the results, right? So that is a great vulnerability. So this is the domain which is like I started this domain during my postdoc. I was the first person to work on started this domain. Now you see like there are almost like 500 papers in this domain. May not be 500, at least more than 100 papers, because last few years I'm not following because I'm not working on this domain. For the hardware security guy, it's very simple because the chip is very simple. So then I also worked in some nanomaterials which can also be used as a VLSI chip. So we worked into it and figure out if this device can also have some vulnerability associated with it. So now I'll move into a simple aspect. I'll try to explain the fault analysis a bit much more higher aspect, so that even if you don't have any background in the hardware security, you will understand what we guys do and how the attack works. You know, you might be knowing ciphers like AES, but you might not be knowing like how this attack works. So what I try to do, I'll try to explain in a high level how this attack works and what are the hardware we use. Later on, if you some of you may not be PhD, so if you are interested, so you can do PhD in this domain, and this is very promising domain. So now, see, this fault analysis started with this example. Suppose so there are two persons, for example, you and the postman, right? So now you are buying something, some toys. Like there are two categories of toys shown here. One is the car, the other category are the aeroplane. So car is cheaper, that's $3, and the aeroplane is plane, which is a $5 thing. Now this Dino is the postman, right? And Jag is you guys. So you are buying something from Amazon, and I'm the attacker, right? I'm Dino. So now, the moment you buy something, right? So you pay the money, and that thing comes from Amazon, and this is most of the time it is anonymous. Like what is inside the device, nobody knows. Like what is inside the package. So you don't know whether it is car or whether it is a basically a airplane. So now I'm the attacker. My query, my objective is to figure out what you bought. But I know you can buy two things. The assumption here, I already know you can buy two things. One is the car, and I also know that if I know you are buying car, then I know what is the price of that car in Amazon, right? I know if you buy aeroplane and what is the price of that aeroplane in Amazon. That is public. So the assumption here, the attacker knows what are the possible things you are buying. The two possible things. One is the car or aeroplane. It's not the third thing like some other toy. So now the attacker objective here is to figure out what you bought, right? So now what information attacker has? So attacker will come to you, and so so what you are doing is that like you will pay some money, right? So you'll pay some money for whatever you bought. So that is that postman guy. You will just pay. Suppose you're buying that thing through postal order, not paying through UPI or your credit card, debit card. So this is again one assumption just to explain. This is like taking you to like 15 years back where you did not have a card, which is not so popular back in those days. So in those days you want to buy, so you have to pay postal order, and then the postman would know okay, how much you are spending. So that is what the assumption. The postman knows how much you are spending. So suppose this is a $15, right? So now the question here, what did you buy using $15? There are two possibilities. So $15, if you buy car, you might have bought 5 car. If you're buying aeroplane, you might have bought 3 aeroplanes. So two possibilities: 5 car or 3 aeroplanes, right? So now he want to just pinpoint exactly what you bought, whether it is 3 aeroplane or 5 car. Now the simplest trick. So this is being used long back, and it was presented. This idea was presented in 2006 FTDC conference. So FTDC, like one of the key conference in fault analysis, right? So in this conference, they mostly talk about fault attack and its defenses. So now what these guys will do, he'll have the package with him, right? So while giving you the package, because you take the money, now it goes to the Amazon and Amazon will give you the package. Now, suppose that Amazon guy is putting all this thing in the package and now give it to you. And now what you can do, you kick it, right? And break some of the toy. Now, how many toy you want to break? That is what way you are injecting the fault, right? You can break one toy, you can break two toys, all the toys, right? Just if you keep on dancing on top of the package, then all the toys will be broken, right? So you have to have an expertise in breaking things so that you'll break the required numbers of toys. So in this example, what he does, he'll just give it to the guy who bought it, right? So now what happened? Suppose one toy is broken. Suppose the guy is very expert, the postman is very expert in breaking things. So he kick in such a way only one toy is broken. So if that is the case, then what? You should get refund. Now, instead of paying $15, now if it is car, how much you'll be paying? $12, right? If it is an aeroplane, uh, you'll be paying $10, right? So now this is the way the attacker figure out what was inside the package, and this is the source of fault analysis. So what fault analysis say is that if you have the fault injection capability, that means you can you can induce a fault in a pinpoint location, then you can actually get a lot of information from the system, right? And the way you inject the fault, that is the crucial thing in fault analysis. So now, what do we do with fault analysis? So see, fault analysis in our case, we should have the chip with us. Suppose I want to inject fault, I want to break your mobile phone. So break means I want to break the security of your mobile phone, then I need to have the mobile phone with me so that I can inject fault into it. I should also be knowing what are the cryptographic system you're running, right? For example, your mail, you are sending a mail, right? If you're sending a mail, so that if you're using the open source email system like IIT, so we use open source email system, then I precisely know in the mail transfer, what is the security protocol, what is the cipher running, right? So now each time you are running that crypto system, I will inject the fault, and based on my fault analysis, I will break that crypto system. Now I have the secret key with me. Now I know the secret key of the cipher that you are using for mail, and that also being used for many other application of your system. So I know the secret key of that. That cipher is broken. Now I actually broke your system because your system security is given by that cipher. So that is being broken. So this domain was started long back in 1996 by Dan Boney, and then later on, Eli Beham, he developed a differential attack and shown much more finer, more a bit practical way. And then Rose Anderson, that's like they have a very good lab in the Cambridge. So that lab is very famous. They actually back in 2000, 2005 and 6, they came up with lot of security vulnerability. They figure out a lot of vulnerability even in the missile system being used by US. There are a lot of missile system there. They use chip, and in those chip also there were some hardware trojan. This guy figure out this Cambridge guy, Rose Anderson, and he has a postdoc with him. Still, he is working as a researcher. So jointly they developed a lot of vulnerability, and because of that they got a lot of funding and a lot of recognition. So So you can think of it started around 2000. Fault analysis they started around 2000, and then still fault analysis is like a very it's a very well known domain. A lot of work has been going on. We have a conference called Chess every year. Like almost like half of the paper published in chips are based on fault analysis, and there are like 10 15 different conferences on hardware security, and most of the hardware security conferences you go, like almost one third paper, half of the paper are on fault attack, and people will show how they use fault attack on ciphers, break different systems. So let us focus on one particular system like AES. So I'll talk about one aspect of fault attack, that is called differential fault attack. So what we do in differential fault attack is like you have the cryptographic chip. That suppose this chip is running your cryptographic protocol. Say you're running a RSA or you're running a AES, some cryptographic algorithm. So if I'm an attacker, suppose I have this chip with me for a while. So most of the hardware attack is done in this way. Like suppose you have the mobile phone and some spy agency want to break into your mobile phone and figure out. So they cannot launch cyber attack on your mobile phone because your cyber security is very strong, very effective. So what they do, they'll send some guy in your office the moment you are not there, and they'll take your mobile and plug it to their device and do all sort of analysis, and they will simply leave your device in your desk. So it's just 5 to 10 minutes. Nowadays, it's like few seconds only. So what happens? Your device was plugged. It was logged. It was plugged to some device the attacker has, and now within few seconds they will actually break your system. Now they pass this information to their cyber guy who is sitting some other part of the world, and now from there they can hack into your mobile phone and extract all the data they want. So, but one thing you must know: these attacks are very expensive, right? Everybody cannot do it. So, like for us, we have some expensive device. Now, one of the major objective of attacker like us is to reduce the cost of the attack, right? So nowadays, like we are doing attack using a few dollar, like maybe $100 devices. So using $100 device, also we can break into chips like IoT devices, like your IoT bulb, that bulb which is connected with Wi-Fi. So we can break into those system using $100 devices. So that is doable now. So anyway, I was talking about differential fault analysis. So what they do, they'll take your chip and give the input. That is, if it is a cipher, they give you the plain text and then run the encryption and get the cipher text. Now what happens is that now they take the same chip and put it in a stress environment. So what is a stress environment? I can tamper the supply voltage, and I can reduce the supply voltage, keep on reducing until it's start performing fault. I mean, like start giving erroneous result, right? And now what I can do, I'll have both the outputs. So I can take the difference, and now I have the difference. Now I can go step by step back, because one thing I must say, when we talk about the attack, right, most of this attack are done on the ciphers, and these ciphers are public. It's not like secret cipher. It's not like Enigma. So most of the cipher being used in different software, like you use your web browser, right? So if you just click, you can't see my browser, right? You only see the output. Yeah, you can't see my browser. So anyway, so in the browser, in the left hand corner of the URL, you see that that lock. So if you just click on that lock, then you can go to and check out what cipher it is used. So majorly it's used public key cipher, and in general it use RSA 2048 bit key, right? So now you see this browsers, or the actually this is not about browser, this is the TLS, that is a secure communication protocol. TLS we use, the cipher used in CLA, those are well known cipher. So TLS is like something which is used by everyone nowadays, right? So even Google use TLS, and that means all the companies are using the same TLS and same sort of ciphers, right? So that means these ciphers are public. Now the attacker knows the cipher, and he has one output which is not faulty, another output which is faulty. Now he will take the difference in the output. Now what he will do, he will go one level up. Okay, in that level he will try to figure out the difference. Now he will keep on going up and up until he reaches to input, right? So now what he can try to figure out, in every level he'll try to figure out the difference. So now if you can do that, then what happen, you are actually working the guy like they know. So you induce fault, you break something, and now you can interpret, okay, like what is there in the box. So I'll show you one attack. So before that, like I'll take like few minutes of break. Like if you have any question, you can ask me now. Otherwise, I'll continue. So far, I just explain like what are the basic attacks, what is this hardware vulnerability there in the literature, right? The known vulnerability I'm talking about. So if you have any question, you can just ask me. If your microphone is allowed to turn on, you can just turn it on and ask me. So I assume there is no question, right? Because it is 2 hours. 2 hours a thing we are supposed to take break and ask the audience for any doubts or any question in it. So anyway, let us continue. Now, if you are Dino, then need to know you should have a way to inject fault, right? So that is called fault injection technique. So there are different fault injection technique in a chip for a chip. So one injection technique is the optical fault injection. So in optical fault injection, what you can do? Uh, can you give me a microcontroller, some Raspberry or something? So yeah, in optical fault injection, what they do, it's actually they use laser beam on top of the chip, and they just like apply laser beam on the chip, some portion of the chip. For example, if you have DRAM, and people have shown that certain intensity of laser beam, if you apply on the DRAM, it can flip the bits, right? So whatever value you have, 101001 something in 1 byte, so that 1 bit can be flipped. So now, suppose this memory is your register in your processor, right? This memory is your register in your processor. So and it has got intermediate result. So now I'll just inject a laser beam on the particular that memory location, and then I can flip 1 bit, and that will create a error, that will induce an error in your execution, right? Because the data got corrupted. So and the result you will be getting finally, that is an erroneous result. So that's called that's called basically optical injection. So now you see this kind of chip, if you have, right, this is Arduino, right? NRF52. So and if you can see, so this is the main chip. So in order to inject fault, what do? We just remove this white, the black portion. Okay. So there are some chemical available in the market. You can apply it. It will just melt this top portion. Now, once you remove this top portion, what happened? Now this chip is exposed. So now, if you have a microscope, you can pinpoint which is representing your memory or your cache memory or your registers, right? You can pinpoint there. That is like too much sophisticated attack. But instead of doing all this thing, you can even like apply a high intensity light. If you apply high intensity light, that will also corrupt some memory. So people have shown it. That Rose Anderson, they actually first shown this thing. So matlab, simply high intensity light you just apply, which you can buy, like a high intensity light means high luminous bulb, and you can apply few with using few dollar, you can actually inject some fault. But those fault is not very precise. If you have laser and you have microscope, then you can inject a precise fault into it. So now this is one way of injecting fault. Second way, overclocking. So now if you have any chip like that, so the moment you buy this chip, they'll say ki, okay, frequency, like the microprocessor 1.4 gigahertz, this has got few megahertz chip. This is a few megahertz chip. What is that few megahertz? That is representing the clock, the digital clock used in it. That is the clock for the circuit, right? So if you've gone through digital circuit course during your BTech, then you must be knowing what is that clock I'm talking about. So now that clock, sometime like in this chip, even in this chip, I think you have access to external clock. You can apply external clock through some of this port, some of this GPIO port. So now if you have that facility in your chip that you can apply external clock, then what you can do, you can give a clock, and in the clock you can give a glitch that is called overclocking. So for one particular cycle of the clock, you reduce the clock cycle in such a tiny that it will become a glitch. Okay, so that means the the time period you are giving to your processor to execute its instruction is so less that it will not be able to complete the instruction. So it will produce an error reverse result. So this is one way you inject fault. This is called overclocking or glitching. And the third way, I already mentioned 2-3 times, that's underpowering. So this device, this device, you have some power supply, right? So this pin, if you have Android phone, so you have the same pin. So you connect this thing to power supply, and I have the power supply through this module like this, right? So module like this. So now what you can do, you can have your own custom module where you inject the USB, and now I can control the power supply to the USB, and I keep on reducing that power supply. At one point of time, it start injecting fault. So this is called underpowering. So now what device you need? For the top one, you need chemical, you need laser beam, sometimes you also need microscope. For the second one, and it's most expensive thing, it requires a lot of money, like people like Rose Anderson and my supervisor, Professor Deepti Mukhopadhyay at IIT Kharagpur. He has this kind of device with him. And for, yeah, and it's very tricky, like you have to pinpoint it. So this overclocking is the most cheapest one. So you need just this function generator. If you go to your electrical lab or electronics lab, you will find some function generator lying here and there. Like if you have any electrical lab, definitely they'll have function generator. And using that function generator, you can build your own square wave, and using that square wave, you can actually generate a clock. And for overclocking, yeah, underclocking, overpowering or underpowering, you need this power supply. Okay, that is also readily available in your lab, so you can use that and you can underpower this thing. I did not mention one more thing. So you have this chip, right, and then you keep on heating it, then also it will induce fault. So we did it during our PhD time. So we use the hair dryer, So we keep on heating with the hair dryer. At one point of the time, it will start producing faulty output. So there are many such ways you can actually inject fault. So now, as I said, overclocking is the cheapest one, and it is also compared to this one, compared to like underpowering. This, where is my mouse? This one, underpowering. This overclocking is much more precise. This underpowering, but overclocking is not as precise as optical, but it is more precise than underpowering. That means you can induce fault in a precise way. You can pinpoint up to a certain extent. So now let us talk about what does it mean by glitch and how it is induced fault. So this required a bit of, like if you have remember a bit of digital logic, digital circuit, and flip flop back in those days. And suppose I assume that you are not teaching digital circuit or electronics or something like that. So if you remember your BTech days digital circuit where you use flip flop, and you remember there was a clock input, right? So now what happened? So this is what your clock, right? So now one of the clock I reduce it. So this is what clock period starting from this one to this one, right? So this is called edge to edge clock. That's a not level clock, edge to edge clock. So this is falling edge versus this falling edge, or this is rising edge versus this rising edge is one clock cycle. So now this clock cycle, I reduce it using my function generator. So now, what is the role of this clock in your circuit design? So the moment I said this chip is of 30 megahertz, that means I can have a clock which can work 30 megahertz speed, right? So, I mean, that many cycle per second can happen, right? So, now what happened is that why can't we have higher cycle? Now, if you have higher cycle, the problem is that in your system, one cycle is defining the time or the delay you are giving uh, signal pass from input to output. You can think that your circuit is just like one particular flip flop. You apply the signal at the input, and the signal will be produced at the output, right? Like JK flip flop. The input is some Q, and then what is that? JK is the input, right? Q is the output. So you apply input, and Q will be the output. So the moment how much time it is taking to get the output, that delay is actually defined by this clock cycle. This clock cycle is defining. So if you have, better circuit, like where delay will be less, and if you have bigger circuit, well, delay will be high. So now this all depend on technology. For example, you if you keep hearing about Intels and all, they'll tell you, okay, your chip is built based on 7 nanometer technology, and some other guy will tell you, okay, his chip is built on 16 nanometer technology. So 7 nanometer technology in general will be supposed to be faster, but I'm just like, for the sake of understanding, I'm telling, although this is not directly related. So this shows the compaction, how, what is the chip density. But you can think of, like, if your chip is bigger, your flip flop, suppose flip flop is 2 dimension and it is much more bigger, so this source to destination time is a lot, then it is taking more time. If source destination time is small, then it's taking less time. Now this length is decided by the technology. So if you have better technology, it will be much more faster. And it is not only technology but also your design. Okay? So let us not go into that. What we consider this clock cycle is actually decides how what will be your frequency, right? So now, or in the other way, if you have the chip with you, like Intel chip, you have 1.4 gigahertz frequency, then you can precisely count what is the clock cycle size, right? So now you are not supposed to run it beyond 1.4 gigahertz, right? If you run it, then it will not give you the correct result. So what we are trying precisely here, we are pushing it to go work on higher frequency. So basically, we reduce the clock pulse here. So that means if you reduce the clock pulse, then frequency will automatically increase, right? So frequency is one by the one. It's like 1 by clock width. So that way you can define the frequency. So number of cycle you have in 1 second, right? So if you reduce the width, then number of cycle per second will be automatically increase. So eventually frequency will be increased. So now, if you reduce it to a proper chip which is already developed, so whose frequency is fixed, now you are like increasing the frequency, that particularly for one clock pulse, then for that clock pulse, the calculation. For example, you have a RISC processor which run one instruction for in one clock cycle. So whatever instruction is running for these particular clock cycle, that instruction will be faulty. So I can assure you that instruction will be faulty. Now, when it will be faulty, that depend on the size of this clock pulse. So I hope I'm able to explain how this fault is being induced by overclocking. So if you understood this part, then you are in a position to inject fault. Now, you need to precisely decide where you will want to inject fault in which particular calculation. Now, if you have the software, you precisely know what is the next instruction. We precisely know what are the all instructions. Now, if you can pinpoint which instruction is getting executed in which cycle, then you can precisely induce fault in a particular instruction, right? So this is how the attacker actually inject fault into the cryptographic chips. So yeah, this is just like I wanted to explain. Like if you have D flip flop, it needs this much of width delay. So in order to get the input and produce the output. So if you reduce the delay for a given chip, then the flip flop output will, you remember the race condition, that the output will keep on toggling. So that will happen, and there is a 50% chance that you'll get the faulty output because that toggling is almost random. And this is some sort of our device. Like we use this function generator, we use a desktop, and we use some here it is pattern 3 FPGA. You can have microcontroller like this. This is also, you can assume this device, this microcontroller, suppose it is running AES. So that AES is running, that we know, and we control the clock and we induce a glitch. Then I don't have access to the internal of the chip. How that AES is getting executed, what is the key, right? That part is not known to me. But what I'll do, I'll keep on injecting fault and produce the AES, try to capture the AES output. And try to see if the fault is, if the output is faulty output. If I get faulty output, then I can launch an attack. So this is few more experimental detail. Let us not go into that. Now let us talk about a bit of cipher. Like don't worry, it's a very one of the simplest cipher. The design is very simple. That is why it got accepted as AES standard. This is called random cipher. So so this cipher is like, it's having 128 bit of block. So it can encrypt 128 bit data it takes as input and produce 128 bit encrypted output. So it has got three different versions of key. So 128 bit key, 192 bit and 256 bit key. So now what happens is that it has four particular function. Actually, it is a three function. So it's sub byte, shift row, mixed column. Let us not go into the details. So sub byte is basically a substitution. You give an input, there is a table. There is a table. I think I have this table. So, right. So if you apply 00 as input, then you'll get 63. You'll apply 01 as input, you'll get 7C. Right. So this S box is nothing but given input, the table corresponding output of the table will be produced as output. Right. So it's basically a table. That's what is S box. So now the next operation it has, it's like shift row. What it does, it's very simple operation. Like you have the shift row. What it does, it actually, you see, it works on 16 bytes, right? 128 bit is equivalent to 16 byte. So 16 byte is stored in a form of matrix in a two-dimensional way like this. Now, how shift row works is like first row remains same, then second row will be shifted 1 byte towards right, third row will be, first row, second row, this one shifted 1 byte, this is 2 byte, and this is 3 byte. If you just match it, you'll figure out this is shifted 3 byte, this is shifted 2 byte, this is shifted 1 byte. So now, what happened? In the shift row, what they try to do, in the encryption, in a layman's way, if I want to explain, is that like you just jumble up the data in such a way so that input, if you have the output, from the output you cannot figure out what was the input. So it is one way of the jumbling, that is shifting the data in row wise. Now you will also do some sort of manipulation in column wise. So in column wise manipulation, it's again very simple. You take one column of the input data, and then you multiply with this matrix and produce the corresponding output. Okay, so this is called mixed column. So you can go to the specification of this AES encryption algorithm, and you can figure out. These are very simple algorithm, very simple calculation. Even you can teach this thing to primary school guys, those who know simple arithmetic, A plus B and things like that. So yeah, so it has 10 rounds. So now let us, like, it has also key schedule. Now what we do is that here we have the chip with us that is running AES encryption algorithm, and I precisely know this encryption algorithm is running for 10 round, or that means like it is using 128 bit key, and I also know this algorithm is running in iterative way. That is one important thing I should mention. See, in AES, if you see this AES, this four operation is called one round, and this round is repeated 10 times for 128 bit key, and 12 times for 192, and 14 times for 256. Generally, I we don't work on 192 or 256. Most of the software they use 128-bit key. So yeah. So now the iterative fashion means, so you will have a circuit which is for one round only, and you repeat that circuit for 10 times, and you get the input, produce the output. That input is output is fed into the input again, and you repeat this thing 10 times. I'll show you in slide. So this way. So this is one round. This box is one round, and now you give the plain text as input and produce the output. After one round, you just repeat, put it back at the input, and you keep on repeating for 10 times. Then your encryption is over. Now you should get the output as ciphertext, right? So now what is our job is to this each round is executed in one cycle. So you target the particular round you want to inject fault. So in that particular cycle, you have to inject the glitch, and it will produce a faulty output. Okay. So now let us see the how fault attack works. So this is what your input. This is a plain text. Suppose in when WhatsApp, right? You know WhatsApp message are encrypted. Suppose you have the WhatsApp with you, and the message you typed, it's say 128-bit message, so it's 16 byte, right? Although you type more than that, like a sentence, but eventually that sentence will be taken and it's converted into binary, and then the corresponding uh, block one first 120 bit will be taken, encrypt, then second 120 bit encrypt, and this way it will continue. So now suppose from the message I got the binary and I have the first 128 bit. So that is 16 byte I have, and I store it like this in a matrix format, right? So now this is the first round. And I know what clock it is using. So what I need to know, I just like switch the your machine's clock with my clock so that I can induce glitchy clock into it. So now I know you are using encryption algorithm. So I will choose particular round. In that particular round, uh, is represented by a particular clock pulse, right? In that particular clock pulse, I'll induce fault, glitch. So that will give you a faulty output. For example, I induce the fault in one of the byte. So now if I XOR this two value, two matrix, right? Directly XOR byte by byte. So then all other bytes are same except the first byte x0. X0 is converted to x0 prime. So now I'll have the difference, say the difference is f. Now, if you go to second round, this difference, because of this mixed column operation, this difference will be spread to 4 byte. Rest of the byte will not have any difference because the fault is not there. So rest of the byte will have the same value for both faulty execution and fault-free execution, same value. So this is for the next round. If you go to another round, if you run for another round, then what happens? This fault will be injected. Okay, let me just show you the picture. Okay, so if you say this is in one round, this different type of fault index. So if you go for two rounds, so fault will be induced in all the 16 byte, right? So that is job of the attacker to at least induce the fault one round before or two round before, so that fault induce at least 4 byte or if possible 16 bytes. So now what happened? Now how the attack works? I'll show you how the attack works. What is the cryptography? We call ourselves cryptanalysts. So now you feel that cryptanalysis means it's a lot of mathematics, linear algebra, probability, statistics, but we don't do much of linear algebra, or probability, or statistics. What we do, I'll show you. So suppose I have this faulty output with me, this faulty output with me. So that C and C, the cipher, faulty ciphertext and fault-free ciphertext. And fault is just induced one round before. So I know in the output I'll have fault in 4 bytes, right? And if I injected one fault here, so I don't know what is the value of F, but I know it is some value F, right? And if it is F, whatever may be the value, So this would be 2F and F and F and 3F because this is because of this mixed column. So every cipher, symmetric key cipher, use some sort of mixed column operations with some other matrix value like this. Okay, I hope my cursor is visible to you. Yeah. So now because of this four possible value, now this value can be represented with the cipher text byte. The C00 is the first byte of your cipher text. And C00 prime, it's like ulta question mark because of I am open I have opened the PPT in different system. Linux, it was prepared in Windows. So that's why some of the symbol change. So it was actually C00 prime. So now I have this faulty byte, right? So now I can represent this 2F with this equation. And this S inverse is basically the table inverse of the table. So now I can have four equations. You see, right hand side, I have C00, C13 all are known because these are cipher text. That's the output I have, right? But this K are the key of that particular round. So that is unknown. That is a secret key. So now I have this equation with me. Now you give this equation to your class 10 guys, like in the school. If you have kids who are studying in class 10 or 12, they know how to solve this equation, right? So you have four unknown variable. Okay, five unknown variable. So this 4k, k and 1f, five unknown variable and four equations. That means you can reduce this to one unknown variable, right? So if you solve this equation, so that complexity will reduce to one unknown variable. So previously, before I attack this, I had five unknown variable f and k00, k013, k22, k31. So five unknown variable each of one byte. And now if I solve it, so this unknown will be reduced to one unknown variable because I need five equations to solve a five unknown variable thing, right? So because I have four equations and five unknown, so it will be reduced to one unknown. So in a cryptographic way, so your unknown complexity was one variable is one byte, so 2 to the power 8 bit, 2 to the power 8, 2 to the power 8, 2 to the power 8, to the power 5, so 2 power 40. So now after solving this, it will reduce to 1 byte, 2 power 8. That means, suppose you had a key which is of 40 bit. Now the 40 bit key is reduced to 8 bit. So if you can reduce to 8 bit, that you can brute force. So one more thing I want to tell you. So this is for 1 byte. If you apply this byte, you will get another sort of equation and you can actually get to know, reduce another set of key bit. This way, you can actually reduce 128-bit key, which is not known to you, and you induce fault and you form this sort of equations and you reduce 128-bit key to just 32 bits. Now 32 bits will take less than a minute to brute force, right? So what does it mean by brute force? So I have 32 possible keys. Previously, how many key possible? I had 128 bit. So it is 2 to the power 128 bit possible keys. Now I have 32 bit. So it is 2 to the power 32 possible key I have, which is much more lesser. So now I can just brute force. That means I can give input plain text and I can output plain text and I can check whether this key is used or the other key is used. So I can try all the key and the key which is giving me the known input output, that will be the correct key. So this is how your fault attack works. And there are many advanced version of this attack. So uh, so this is the most fundamental part of the fault attack. And if you ask me what I did during my PhD and afterward in fault attack, so what we do is like we develop attacks using different sort of fault. We call it fault model. So now in order to check whether this attack is practical or not, that is defined by your fault model. So fault model defines like where you injected the fault, how many bytes of fault, So the simplest possible fault model is you inject, if you have 32-bit architecture, so your simplest fault model is 32-bit fault or 4-byte fault. So 4-byte fault is easy to induce in 32-bit architecture as per the fault injection technique I shown. So we try to reduce the complexity of the attack. We try to simplify the attack, and we also try to develop the best possible attack. So still in the domain of differential fault analysis on AES, we our attack, like the thing we proposed back in during my PhD, still it is considered as the best known attack. So I got like around 500 citation in that paper. So yeah, so I think we should stop here. Uh, Meanwhile, if you have any question, it's around 4 o'clock now, and based on your question, we can continue and we can look into possible aspects. Like if you're interested in research in this domain, hardware security, also you can talk about. And if you want to know more on the domain of no security, you can still ask me. Yeah. Uh, I think I should stop here. If you go beyond this, then there are much more complex equations, and that will be more difficult for you to understand in one day, until unless you have a little bit of background on fall attack. My objective of this talk is to give you some flavor, like how this attack works in a high level. I did not go into equations, how we got the equations, but what I wanted to show is that, like, if you have equation, if you can form an equation like that, therefore you have 5 unknown and you have 4 equations, so definitely unknown space will be reduced. So that is what the technique being used by the attacker like us, and we uh, reduce the key space. We call it key space. If it is 128-bit key, the key space is 2 power 30 to 2 power 128. That's a very big number. That's like even like bigger than all the atoms, not atoms, all the like electrons in the universe together. It's not as big as 2 to the power 128. It's a huge number. Yeah, so I just wanted to give you some idea of hardware security, which is like very important field in the domain of blockchain nowadays, because blockchain are majorly based on crypto token. There's a lot of people like don't remember, and they don't want to remember even. And you will keep your crypto token somewhere in the safe, and then even if somebody kidnap you, you don't remember anything. Like, so that is one more level of security you are providing. Yeah, now I'm ready to I'm open to take questions.
Mahendra sir, you have a question, please ask.
Good evening, sir.
Good evening.
My name is Mahendra Singh Chauhan, SSBT Engineering College, Bamburi, Jalgaon.
Okay.
I have one question, sir.
Yeah, please.
It is possible the fault injection technique from remotely, or it will be performed by a hacker?
Yeah, so remotely it is possible. Yeah, so that is very interesting question actually. Uh, I generally give an example of that during my talk at the beginning of the talk. So actually, fault injection was become very famous back in 2000, around 2000. There was a Pentium chip, right? There was a Pentium chip, and in one of the version of the chip, they have a fault in it, right? So an attacker knew that chip is erroneous. Okay, so now what he did, he actually push your code. For example, TLS you are running. So in TLS you are running AES or RSA. So he push your code to run on that faulty part of the chip. See, fault means what? So you have a chip means a lot of things, right? So maybe in one particular register you have the fault, and it gives error once in a while. Now, there are different sort of error, transient fault, a permanent fault, but this was kind of transient fault. So now you, this error come at some point of time. Now you have the code that is running in that chip. Now, sometime you run the code, it will not have fault because the code was running in different using other register, not this register, right? So that attacker figure out some technique so that you can push that code to run on using this register. The moment you run using this register, so fault will happen. So these kind of attack are remotely triggered. Okay, so the attacker precisely know. For example, he knows that the code you have written for AES is a faulty code, right? But this fault occurs only for given certain input, not for all the input. So in that case, if the attacker figures out, so he can do the remote attack, he will induce that particular input to your encryption algorithm, which is running some other part of the world, and then the fault will be injected. So remotely it is doable, but the hardware thing we talk about, it is majorly physical attack. So you have to have the device with you, then only you can attack.
Just like the attacker must be attack on the CMOS program, just like on motherboard. It will
Yes,
be possible to damage the OS, their basic OS of CMOS.
yeah, so in CMOS, CMOS is the technology basically. That is your ROM you're talking about, right? So where uh, the boot, the post power on self-test thing will be there, or you're talking about bootloader. So even if you load the boot, lot of encryption, decryption happens just to verify the your your boot module of the operating system.
Correct.
To make sure, nowadays we use secure boot, right? Just to make sure that your operating system is actually a valid operating system. It is not the compromised one. So that also requires a lot of encryption decryption, and that happened during the booting process. And for that also they use this chip. So you can actually induce fault into that chip so that during booting time it will break the system, and now you can load malicious operating system, and your system will not be able to verify it as malicious.
Okay, sir. Okay, sir. Thank you. Thank you.
Yeah, thanks for the question. Are there any more questions?
Is there some questions from the participants?
Sir, I have one question. How can hardware wallets enhance the security of cryptocurrency? Like in
Sorry, can you repeat it?
blockchain systems, how can cryptocurrency storage can be enhanced?
Yeah, so now, as you know, see, all this attack I was talking about at the beginning of the talk, and then I gave a specific attacking technique. So all this attack, if you do not have this the security measurement against this attack, then your crypto token is vulnerable to these sort of attack. So now, uh, people had to propose solution against these sort of attack. For example, if you want to protect against fault attack, so one of the simplest technique is that, like, you do not allow glitch, right? Okay, just 3 days back we are having a discussion with a very senior Intel scientist who happens to be from UP, and sees our director's friends. She came to India, and I mean, she was originally from Bhilai, and she came to India and came to Bhilai. So our director invited her, and she joined us, and we had a lot of discussion on this. So in Intel chip, what they try to do is that they they will not allow you to inject glitch. So glitch detector, they will have, the first thing, they'll have glitch detector. Second thing, what they do, they use guard band. So guard band in the sense, like, your processor is allowed to take this is maximum frequency of this one. Okay, but internally it can allow much more than that. So that is the thing they call guard band. So guard band is not being used to secure your system against fault attack. Rather, it is part of the design, because sometimes you manufacture a chip with a target frequency, right? But due to variation in manufacturing, you may not be able to achieve that frequency, right? So that's why you use guard band. So if you have guard band, that means like maximum frequency is this. Actually, you declare much more less frequency than the actual frequency of the chip, actual frequency of the expected design. For example, in during the design process, if you expect that your chip will work for 10 megahertz, after manufacturing, you should not be telling the customer that it is working on 10 megahertz. Rather, you should talk that it can work up to 6 megahertz. So now, rest of the 4 megahertz will be treated as guard band. So guard band, because some of the chip may work in 10 megahertz, some of the chip may not, less than, but it cannot be, as per their calculation, it should not, there should not be any chip which works less than 6 megahertz, right? If that is the case, then again you have to increase the guard band to up to 5 megahertz. So that is what they do the protection. So now for power analysis attack also, like you have to incorporate in such a way, so you have to add some random computation so that this power profile become very random. So they do this thing using like one of the major technique they follow is the masking technique. So using masking technique, you can protect up to certain extent against power analysis attack. So if you do not protect against this attack, then your crypto token are vulnerable to hardware attack. That means if you forgetfully leave your crypto token someday with your friend or unknown, get access to it for maybe for few seconds, then he can break your crypto second, make a clone of it, and he can steal all your cryptocurrency. He can steal all your cryptocurrency. So that is what the concern here. So and our security, our research is focused on how we say that given a chip is secure or not, right? So for that we keep on developing newer and newer attack, and nowadays we have machine learning also. Using machine learning, we can even improve this attack much more further. Like you need less number of uh, attack input, less number of data to launch this kind of attack. Yeah, I hope I'm able to answer your question.
Yes, sir. Got it.
Are there any more questions?
No question, sir.
Okay. If there is no more questions, shall we stop here?
Yes, sir.
Okay then. Yeah.
So, heartfelt thank you to Dr. Sk Subidh Ali for sharing your valuable insights today. The participants truly got inspired a lot from the dedication, your achievements, and presentation served as a true inspiration. Thank you, participants, for your engagement. In closing, let's carry forward this spirit of learning and innovation inspired by today's session. Thank you, sir, and all the attendees for joining this mesmerizing session. Thank you so much.
Thank you, Priyansi. Thank you for inviting us. So I would like to add few more thing. Like most of you are faculty, and the attendees are generally faculty from some colleges, right? So and you might not be that much familiar with IIT Bhilai. Uh, IIT Bhilai is just like started in 2016. So now we have full-fledged MTech, BTech program. We have data science in BTech, MTech, and PhD. We have electrical department. We have electronics, and we also have mechanical and few other streams like mechatronics, EV, and material science is also started. And we have very active PhD program, and we want that the neighboring our state or the neighboring we should get students from the neighboring state, but most of the time the candidate do not have the idea like I mean like they 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 may not be knowing like IIT will also have PhD program, and they hire people from the neighborhood. So I would like convey this message to you. If you have meritorious student like who are like interested in doing PhD, right? So we for PhD and research, we never look for the best of the best student. Rather, what we look is the student who is interested in giving some dedication, like some consistent work, and uh, and our PhD criteria, selection criteria is also very simple. Like if you have BTech student, if the student have any gate score, like valid gate score, then he is eligible to apply for PhD, and in the full time PhD he can apply, then he'll get the stipend. Okay, this part is also not known to many students. So if you have BTech student, please convey this message to them. If they have gate score or net valid net, then they can apply to regular program and they can get the stipend for 5 years and they can continue their PhD, get the degree from IIT Bhilai. If you have degree from IIT, then you can easily move to abroad for postdoc and you can even settle down there. And like if you have MTech, right? So then you don't need get score, you can directly apply and you are eligible, right? And our selection process is based on interview and written test. So we'll have first initial written test that is conducted in the same days. I mean, there is no cutoff for written. So whoever comes for interview, they appear for written, and whoever appears for written, they give interview. So based on the written and interview score, we select. We majorly look for fundamental, right? That you teach in your BTech courses. So we majorly ask for fundamental data structure, algorithm, and computer architecture, organization. So we don't need people to come and say they know like deep learning, they know machine learning, they know VLSI design. We don't want. We want very basic subjects. Like if you feel like if you have some student, you always encouraging them to apply. So either they should have MTech or BTech with GET or MSc in computer science. I'm talking about computer science, MSc in computer science with uh, MSc or MC in computer science with NATE or GET. So any one of this, if you have, then you are eligible for PhD program. So we have very strong PhD program, and there is another aspect of PhD program. We have a lot of project opening, right? You might have a lot of students who are interested into work in some development projects, some R&D projects. So if a student work with us for maybe 1 year or 2 years, so with that experience, they can the starting package is generally around 10 lakh, right? If we select some student for our project, if they work for the project, then uh, for 2 years experience, they can switch to a related company, and I can assure you that starting package will be around 10 lakh. Right? So that kind of facility we have, but unfortunately, these informations are not particularly known to the student around this region, and sometimes they feel like okay, this is IIT, they will never select us. So that is not the case. We all it is like uh, we want the student, but there are meritorious students, they don't know that we are looking for them, right? So you can work as a mediator, you can
Yes,
convey
sir.
this message to your BTech student, and so that they should apply. See, we have this winter session going on, so within a month we have an ad, right? And also you ask your student to go through our website, and there are some recruitment portal and there's project opening. So in
Yes,
project opening, the salary is almost same as the PhD stipend. So now, even if they join the project, if you are 2 years in project, then you are eligible to do the PhD, and you will get the funding from the project for doing the PhD. So it's like very good opportunity for the local student around this place, and it will also good for you. The more and more student coming to us from your institute, so that research mindset will be created in your institute also, and then more and more BTech student will be very keen to do research, and then they'll come to you for different projects, right? So that way, like the research culture will improve a lot. So I hope in recent future will get students from
yes.
you. And if you have
Surely, sir.
any query, you can share my email ID. I will be happy to help because I am the PG coordinator. We call it DPGC. So I am the PG coordinator for computer science and data science department of IIT Bhilai. So if you have any query, any student can directly approach me, right? And I'm happy to respond. I always respond. Okay. So
Surely,
thank you
sir,
from my
we will
side.
share this information with our students as well. And I'm also happy to share that just in the last week, we had Dr. Rishi Ranjan Singh from
Okay.
IIT Bhilai at our campus
Oh,
for
great.
the guest lectures to our students.
Okay, okay, great. So
Yes,
he
sir.
is very good friend of mine. Yeah.
Yes, sir. Surely,
We
sir.
joined almost at the same time.
Yeah.
Yeah.
Thank
Okay.
you, sir.
Thank you all. Thank
Yes.
you for
Yes.
invitation.